relationships with this pair, going back literally to 1973. We're going to talk about here. This will be a part of the presentation. I want to format the disc. So the title of my talk is 1976, It Was a Very Good Year. Most people probably remember it because it was the bicentennial. I contend that there is a more important reason, that's why we're here today. It starts actually just before this. It starts back in 1973. I was a co-op student at Cornell. And that summer of 1973, I met Jim Thorp. Jim was the professor of one of the courses during the summer session, and we had a great time. In fact, we bonded as a group. I tried to find Rachel, but I didn't know what she got lost to. So this was 73. Immediately after this, then, I proceeded to work for AEP at 2 Broadway. And this is down in New York City. And my first day on the job, the engineering manager comes to me and says, "Mark, you're going to computer applications." And I said, "I really don't like computers. Can you put me anywhere else?" And they said, "Nope, you have to go there." It's the first day on the job. I sit in the office, and who comes in but Arun Phadke, who just happened to be coming to visit the person who I was sitting with in the office that day. And not only that, I had across from me, Meyer Sasson, who is well known in the EMS business, and also George DePazzo, one of the developers of the original state estimation concept. So I had a very, very interesting upbringing in my very, very early youth. So at this time, I had met the 2 individuals that would be eventually joined, but there was one other person who also knew both these individuals. And this is the matchmaker. This is Larry Dwan. Larry Dwan was a Cornell graduate himself, and he knew both Arun and he knew Jim. And so he was he was the one that pulled Jim in for a sabbatical, and that sabbatical was in 1976. So in about the June time frame, Jim Thorp shows up in New York City, and this collaboration starts. Now, if Larry was the matchmaker, then we had the marriage counselor. Stan was the one that identified the issues that this team had to work on. And without the application background, a lot of this would not have happened. Stan was able to organize this, we'll call it a clandestine team, that was actually working on digital protection and control starting back in about 1971 time frame. And once Arun and Jim came together, there was immediate collaboration on numerous projects. This is one I pulled up. This is Arun's handwriting here on this memo here. This is a 1980 memo, Arun. And there was collaboration between Jim and Arun. Like at the time, we actually had an analog computer. This is before we had all the nice simulation software. And so Jim then sat together and put together the complete analog model for CT saturation in power systems. This was all done before, this was analog computer time frame, actually. So what was interesting for me as a young student is seeing the hands-on aspect. And everything had to have validation in the physical world. So we monitored everything, we captured data. We had a light beam recorder. So when we ran tests, we would run the light beam recorder and capture waveforms. In fact, I still have several of the papers that are still not quite totally faded out. But this is one here showing CT saturation that was developed on the analog model by modeling a CT. On the analog computer. Jim was fun to work with. He was very, very succinct. We had this one paper come in, and I asked Jim, "Jim, can you put some comments on this paper?" These are actually Jim's handwritings. He never used these symbols in class. I'm sure they have some meaning, but again, the message was very, very clear. So this is one of the ones that I saved, actually, in the analysis. I have a folder of these things, actually. I have quite a history going back over the years. I won't mention the paper they analyzed, but I still have that around, too.
What is the top line?
Well, isn't it clear? This is some language beyond Greek. Then Arun had his aces. He never quite identified how he spelled that, but there were several of us who worked in the lab. Actually, this is the picture of the laboratory where the synchrophasor was discovered and identified. This was the model power system on the 19th floor of 2 Broadway in New York City. This other fellow here is Ted Lipka. And I'm going to point out, see that scope there? I still have it in my basement. So whenever the Phadke Thorp Museum comes up, I will donate it. But we modeled the power system. We had, what was very unique here, we had a wound rotor induction motor. I mean, GE introduced the variable frequency transformer probably about 10 years ago. 30 years ago, we had it in New York City. And with this wound rotor induction motor, we were able to create angular differences between the 2 sending ends of a transmission line. In fact, one of the things I put together was a little motor that would automatically spin and turn the motor back and forth to create oscillations. And in fact, if you go back to the original synchrophasor paper, you will see a modulated 60 Hertz waveform that was generated using that wound rotor induction motor. The synchrophasor starter was the PDP-1170. This was the computer on which the first Fourier transform to do computer relaying was implemented. It was quite a challenge. We sampled voltages and currents at 12 samples per cycle. No floating point. Everything was done in fixed point integer math. As a result, at 12 samples per cycle, the coefficients for the Fourier transform are very, very easy. It's 1/2. This is a very easy number to compute. 1 is a very easy number to compute. The only strange coefficient was 0.866. And we resolved this by having 2 channels in the A to D converter, one that read straight gain and one that read a gain of 0.866. So we multiplied in hardware instead of having a digital signal processor, which everyone else has today. A lot of the fundamental concepts of today's digital relay architecture were developed early on at AEP. This picture here actually shows early process bus concepts. So AEP had the concept of a process bus. This is about circa 1980. What you're seeing here in this outline is what we call today a merging unit in the IEC 61A50 world. So we were actually way ahead of the curve as far as predicting where the technology would be going. Digital fault recorders. Jay was out there for one of the first ones. Actually, the first one was probably the System 7, where the data was captured from the System 7 mini computer was located in a substation in Roanoke, Virginia, and it had something called remote job entry, where if a fault was captured, it would call up to New York City from Roanoke, Virginia, and overnight they would upload the data at 300 bits per second. Technology really got better a couple years later when we were able to upgrade to a 600 bit per second modem. GPS came into, well, when the Fourier was used, it was identified, in fact, where the synchrophasor, of course, comes from, is identifying that the Fourier rotates as the frequency of the power system changes. So what was needed was a very, very stable clock. In fact, I like telling the story of GPS, and I asked the question, to whom do we owe the most for GPS? And the answer I give is the Russians. In 1957, they launched Sputnik. And Sputnik was basically a bomb where they removed the bomb portion and put in a radio transmitter. So as the radio's flying around, you have a Doppler shift. Given the Doppler shift, people on the ground were able to track the position of Sputnik by looking at the Doppler shift. Somebody figured out, well, gee, if we know where we are and we can tell where the satellite is based on the Doppler shift, the inverse should be true. And inverse being, if I know where the satellite is, I can figure out where I am. The second reason we thank the Russians is that in 1983, Korean Air Flight 007 strayed into Russian airspace, and the Russians shot it down. Shortly after that, President Reagan opened up GPS to the world. And so we thank the Russians for enabling that there. This was the first GPS clock that was purchased by AEP. This is the purchase order for that, by the way. Cost $13,727. I will point out that you can now get a silicon chip that includes not only the GPS, but also the 1588 Grandmaster capability for about $10. So we've come a long way in this area. We saw a lot of the finished presentations by Manu and others of the whole concept of how do we use synchrophasors. This is the first sketch. This is Aaron's handwriting here, if you recognize it, Aaron. This was 1988. We sat down and we laid out the architecture for a synchrophasor system. In fact, the world's first phaser data concentrator was a Microvax 2000. And we laid it out so we could have as many as 8 PMUs coming into one Microvax. In fact, another story, in the original implementation, in fact, let's go to the next slide here. The first communication link was on a 4800 bit per second modem using Paradigm modems. That's actually the name. This is the actual sketch. Very, very small bandwidth. So that's why the C37118 protocol is as compact as it is, because we had no bandwidth. So everything had to be in binary, minimal amount of data. In fact, one of the major changes that was done was in the original first implementation, there were 6 fields: year, month, day, hour, minute, second. I went to our programmer on the Microvax and I said, I want you to sort all these fields. He goes, you're crazy. And this is where we came up with the concept of using the network time protocol, second of century. So with one 32-bit integer, we were able to eliminate 6 fields in the data message and significantly compact the message that was sent out over the modems. Here's the first visualizations. Again, this is Aaron's handwriting here. And we see the relative angle synchrophasor plot. We see the magnitude plot. We see the angle over time plot, and a time error plot. In fact, no one's implemented the time error plot yet, Aaron. They haven't seen this presentation yet, probably. Why? And this, of course, is the first PMU. Now, this was put together by this team. Now, this is really good. These are students, but yet they were disciplined enough. It must have been the mentor they had, that they put out an instruction manual for the PMU. And this was by the crew here. In fact, we have 2 of them here, Mr. Begovic and Centeno Virgilio are here. And what I do need to point out is that we received the unit. Some modifications to the software had to be made. In fact, I think we rebuilt most of it. But it did work out there, actually. And the first installation, here's the world's first phaser data concentrator. It was a DEC Microvax. We had 70 megabytes of storage. And that was good enough for about 30 days. Now, at this time, we were only reporting at about 12 messages per second. The first installation was in a 765 kV substation known as Marysville, which is just due north of Columbus, Ohio. So this is where the first PMU was installed. The second one in the world was installed, I think I beat you out, Ken, on this one here. This was, we'll see in a minute. I don't know if you have your dates on yours. The second one, though, was installed in Rockport, which is in southern Indiana. Now, this is I'm going to probably say the world's first PMU plot. And I got dates on here. So this is June 14th, 1989 was when this plot was actually produced. And it shows the angle and frequency. This was early days. I did a basic differentiation here. There was no averaging, and so that's why you see all the spikes in frequency. Frequency doesn't really do that, but my math did. The group we had was we had a very, very congenial group. We became really a large family. We would get together quite often. Now, notice Jaime. He's looking at his future boss there. He doesn't realize it yet. In fact, notice he's still looking at the future boss in this other picture here. I don't know what this says. Maybe he was prescient about what was coming. And then Kasum, and of course we have lost one of the team there. And Aaron got to know the family very well. This is my daughter he was holding at the time there. And we adopted Gary Michael as kind of an adjunct member to the family. We also had fun. We had a Tektronix 4054 plotting system in the building. And I came to Aaron one day and said, hey Aaron, there's this neat curve, sine z over z. How do I map this onto the plotter? So Aaron sat down with me and we went through the mathematics. And about a half hour later we had the math. And then about an hour after that I had this plotted on the Tektronix. And it was a neat little plot. But this is the kind of relationship that we had, able to go in and talk about all kinds of different things, not just synchrophasors. Interesting, I went to Google and searched images. I searched an image on Jim Thorp. Who shows up? But it works both ways, because then I went to search for Arun Phadke, and who shows up? Jim Thorp. Now, this says a lot about the relationship of these two guys. Now, I tried a third search. I said, what if I search on Phadke and Thorp? What shows up? A happy penguin. Now, Google has some way of coordinating this, but this is what literally showed up when I did the combination search. So, now, as a result of this 1976 collaboration, there's a range of papers that are fundamental today in all digital relaying. So there was work done on a flux-based current differential. There was limits to impedance relaying. There was ultra-high speed, which is used today in many devices still. There is transformer differential, voltage restrained, which no one does this one yet, I don't think. Never really got used. And then, of course, the main one was the one on the synchrophasor, which is the tracking of frequency. I'll point out, Aaron threw me into the lion's den on this one here. This was presented at the San Francisco IEEE meeting in this year, which was '82. And he said, I worked together on putting together the presentation for this, and it came time to go out there, and Aaron says, okay, Mark, you're doing it. He sent me out there alone to the IEEE meeting, and I was the one that actually presented this paper at the IEEE conference back in 1982. So anyway, yes, 1976 was a banner year for many, many reasons. Aaron and Jim, we thank you for your dedication and for a great team effort that you put together here. And this is the picture from, we've heard the reference to the Franklin medals. This is the group picture. They do dress up very nicely. I thank you all very much.